Hello, my name is Deepo Debnath, and today I'll be talking to you about my Honors Capstone Design project on improving intravenous drip control in Ghanaian hospitals and clinics. The faculty advisor for this project was Dr. Melissa Roble, and some of the work for this project was conducted in partnership with the student organization MHEAL. So a little background about this project. The problem and need for this project came from U of M's Global Health Design Initiatives, or GHDI, needs assessment trip to Ghana in summer 2016. Students did needs assessment at Korlembu Teaching Hospital in Accra, Ghana, and recorded details on clinical needs that they observed. Something that stood out was issues with IV drip controlling and monitoring. So IV is short for intravenous, and in a clinical context, it refers to therapies given to patients in which a needle is inserted, usually inside their elbow or the back of their hand, to administer drugs or fluids directly into their bloodstream. Now, what we see on the right side of the slide here is a roller clamp, which is a small plastic piece through which the IV line runs, and it's got a wheel that gradually compresses the tubing as it goes down. Now, in high resource settings like many hospitals in the US, infusion pumps are often used to carefully lower or administer a constant volume rate of fluids to patients through IVs at a constant rate. However, in lower resource settings, roller clamps themselves are used as the rate setting apparatus, where a nurse will pinch the tube slightly with the clamp's wheel until they observe that the drip rate is where they want it to be approximately. Well, unfortunately, roller clamps are pretty imperfect. IV drip rates sometimes change during a 30 to 45-minute IV administration, and nurses sometimes recount and readjust drip rates 2 or 3 times during a single administration. When there's a high volume of patients, which there often is at the major hospitals in Ghana, this is a time-consuming and overwhelming process. And just to add, drip rate changes pose dangers to patients because they may be receiving too much or too little of whatever it is that they're being administered. So drip rate change can be caused by a few things. One is roller clamp drifting, in which the IV tube presses back on the clamp's wheel and causes it to loosen up. Other causes include patient transportation and movement, as well as patient tampering. So over the past few years, MHEAL Team Flow has been working to develop a solution to the need for an improved method of IV drip rate monitoring and controlling for hospitals and clinics in Ghana. I'm one of the project leads for Team Flow, and we've been working with an emergency nurse, Mr. Emmanuel Ashumpong, at Komfo Anochie Teaching Hospital, or CAF, in Kumasi, Ghana. One of our past team members actually went on the GHDI trip to CAF in 2019, and she was able to bring back more information that was really useful for Team Flow, as well as for this capstone. For this capstone project, I opted to narrow the scope of what Flow is doing and focus on the controlling aspect of IV drip rates, and in particular, improving the roller clamp itself. That was the aim of this capstone project. There are a few existing solutions that could be useful right now. Both the Dialaflow, which is on the left, and the Exadrop on the right, are mechanical solutions that pinch tubing in a way that's more robust than current roller clamps, but at CAF they've said that these solutions come with their own tubing. Which is not ideal for them because they already have supply chains set up for the tubing that they use. These solutions also aren't reusable since they're permanently attached to the tubing. So the recs and specs are paraphrased here, and we determined them from conversations with Mr. Ashumpong and GHDI interviews. Our partners want a less than 10% deviation from the initial drip rate and for the solution to take less than 10 seconds to attach or adjust. Additionally, the solution needs to be implementable in low resource settings, so we determined that it should cost less than 10 cents per use, whether it's reusable or not, and be compatible with current IV systems. In addition to this, we want it to be able to work with different dimensions of tubing. During concept generation, I focused in on roller clamp interfacing solutions since these would give more insight into what exactly it is about roller clamps that make them fail in the way that they do. But I was open to doing this in a totally novel design or repurposing materials or currently existing solutions. This is actually where COVID-19 was a big factor, since it was important to keep in mind that if we wanted a more complex solution here, then it might just need to be modeled in CAD or computationally tested. Whereas if we used a more simple solution, then we could possibly physically test it. Ultimately, brainstorming and weighing ideas against each other led to the purchase of Velcro zip ties. These ties could be very quickly looped around the roller clamps and fastened right above the wheel, where it tends to start budging to secure the wheel in place. Um, Other ideas that were considered were using tape or rubber bands, or even 3D printing some sort of custom housing to secure the roller clamp's wheel. But after kind of weighing the pros and cons of each potential solution against each other, we decided to proceed with the Velcro solution. Now, it wasn't just one Velcro solution that were tested. We actually tested two different Velcro solutions. One was just the Velcro loops themselves, and another was a Velcro loop, but with a rubbery material on the inside to provide some more grip. If you've seen those oven mitts with the sort of silicone ribbing on them for grip, that was the vision here. I applied a strand of hot glue and I let it dry, which had a similar effect. There were two things that were tested here. One of them, which was ease of use, to see how quickly someone could implement this if given the task. And I asked 6 individuals to try this 5 times each. Remember that one of the specifications for this task was to take under 10 seconds on average. The other, I would say, more important one was drip rate testing, where I hung this IV bag up in my room, filled it with water, and ran control and experimental trials with it. I always used a starting drip rate of 36 drops per minute and counted drip rate every 5 minutes for the control, the Velcro only, and the Velcro with glue treatments, and recorded the drip rates. I did this 5 times each for each condition. So for the ease of use testing, 4 of the 6 individuals were able to attach the zip tie, on average in around 10 seconds. And something to note is that the second try was usually around 2 seconds faster than the first across individuals. So learning how to do this the best way possible happened pretty quickly. We also compared the average drip rates between each group at 15 minutes and at 30 minutes. Here we found that there was a significant difference in the drip rate between the control group and both of the treatment groups, but that there wasn't a difference between the treatment groups themselves and their effectiveness in mitigating drip rate changes. Significance was determined here using one-way ANOVA. We also saw that there was significant increase in drip rate over time for the control group, but no significant increase over time in either of the treatment groups. Significance here was determined using repeated measures ANOVA. It's also good to note here that on average, both control groups managed to keep the drip rate change from the initial to under 10% over the 30-minute testing period, which met another one of our design requirements. One of the most profound reflections that I'd had from this experiment is that COVID necessitated that we come up with a resourceful design, which ended up yielding a simple but, as we could see, pretty effective solution. The Velcro loop is cheap, easy to manufacture, easy to distribute, easy to use, reusable, and it was effective under the conditions tested. In the future, I'd definitely like to make improvements to the experiment, like starting with the same IV bag fluid volume with every single trial, for example. I'd also like to go back to the drawing board and consider the other factors that cause drip rate changes, such as patient movement or patient tampering, as we discussed earlier. And finally, I'd like to expand the scope of this project to IV controlling solutions in general. Team Flow, which I'm a part of, is actually working on both monitoring and controlling. Kind of as a final note here, the biggest takeaway that I had from this project is that effective design is often simple design. If it wasn't for the limitations this semester brought, I likely would have gone down a much more complicated path of making something novel and doing CAD and some more complicated assembly, which would have been a really good technical learning experience. But we could see here that something that's so effective was also really simple. It's a good lesson that I will continue to carry with me. Thank you so much for listening in.